Hey guys, welcome back to Explore Electronics. Here let us see a model question paper solution for digital system design using Verilog subject BEC 302. The first question, design a logic circuit that has 4 inputs and output will be only high when majority of the inputs are high. Use K-map to simplify. You can see a majority circuit here, the block diagram. This block diagram says when the majority of the inputs are high, then only output will be high. You can see the green indication here in the truth table. Where the majority of the inputs are 1, we have taken it as 1 as output. So for these things, if you put into a K-map and get the expression y is equal to BCD plus ABC plus ABD plus ACD is the expression we got. If you realize that using basic gates, this is the logical circuit. The next two questions, twin Maklowski method and K-map simplification of this is updated in the other video. Define the following terms with example: min term, max term. Min term, when a Boolean function or logical expression is expressed in standard sum of product form, then each term of the expression is called min term. You can see here, if you take an example of two variable, the min terms are like this. M0 will be A bar B bar, M1 is A bar B, M2 is A B bar, M3 is AB. Similarly, if you consider a Boolean function, it is in the form standard product of sum, then we call it as a max term. Each terms are max terms. So the max term for two variable is like this: A plus B, A plus B bar, A bar plus B, and A bar plus B bar. Place the following equation into proper canonical form. So the two expressions are given here. The first one is P is equal to f of ABC, A B bar plus BC. Here in the first expression C is missing, so we need to add C plus C bar and we need to multiply. In the second half of the expression we have BC, A is missing. So we need to add A plus A bar with this. So multiply these things and finally min terms we will be getting like this. Then the second expression, A plus B into B bar plus C. Here the first expression will be missing C, so we need to add plus C into C bar. The second expression missing A, adding A plus A bar. Then we will be getting the final expression in a proper canonical form like this. Then design 2-bit magnitude comparator, write the truth table, relevant expression and logic diagram. Here is the 2-bit comparator circuit truth table. 2-bit comparator in the sense we need to take A and B as 2-bit inputs. So the different possible combinations are written over here and the outputs also written. When A is equal to A less than B, when A equal to B and A greater than B. So these are the expressions we get from the truth table simplification. You can use K-map for simplification. That gives you the simplified expression for A greater than B, A equal to B and A less than B. And here is the implementation of that using basic gates. Implement the following functions using 3 to 8 decoder, 3:8 decoder. 3:8 decoder, as we know, will be having 3 inputs. So here A, B, C are the inputs given. Here also we need to take A, B, C as inputs. And the implementation will be like this. 1, 3, 5 are the terms given here. So the first term of the output, third and fifth can be connected together to a multiple input OR gate. This gives the implementation of the first given expression. Similarly, the second given expression also implemented using 0, 1 and 6th positions to a OR gate. It is very simple and these questions will be asked in the exam for sure. Explain 4-bit carry look ahead adder with neat diagram and relevant expressions. A 4-bit adder can be a 4-bit ripple carry adder or carry look ahead adder. Here carry look ahead adder is asked. Both are very important in the exam point of view. You need to write this carry look ahead adder circuit, or you can write directly this, and the expression for carry need to be written with respect to propagate and generate signals. So here G corresponds to generate signal and P corresponds to propagate signal. Here you can see P will be generated by using an XOR gate and G will be generated by using AND gate. So this is how we need to explain how the carry look ahead adder works against ripple carry adder. Then implement the following boolean function using 8:1 mux and 4:1 mux. The function is given like this. So write the truth table first. Here you can see we can since it is a 8:1 multiplexer, we have 8 inputs and 3 select lines. So since the given expression is a 4-bit 4 variable expression or function, out of those ABC can be our select inputs and D can be our data input. So if you look at the truth table, ABC is 0, 0, 0 in these two cases. Means when ABC is equal to 0, 0, 0, I0 will be selected as output. So we need to look for what is I0 here. I0 is with respect to D we need to see. So y is equal to 1. Since y is equal to 1, irrespective of D, we can connect I0 to 1. The other way is that putting into the table like this by taking D is equal to 0 and D is equal to 1. D is equal to 0 corresponds to D bar and D is equal to 1 corresponds to D. And I0 to I7 you can see over here. And what are all the values they have given? 0, 1. So both are there here. So it is not D as D bar, it is 1. Here you can say with respect to I1, there are 2 and 3 are not there. So you can take 0. Here only 5 is there in the expression. So for that we get D. And similarly here 6 is there in the expression. So it is corresponds to D bar. And 8, 9, there are no minterms. So it can be, this will be 0. And similarly I5, I6, I7 can be found. And then we need to connect that into a 8:1 mux accordingly. So here you can change this I4 which is connected to 1 as a wrong connection. We need to connect this to 0. This is 0. This is how we can implement using 8:1 mux. So then the next thing is we need to implement it using 4:1 mux. In the 4:1 mux, again 2 select lines are required. You can take AB as select lines and 4 inputs are there, I0, I1, I2, I3. So CD becomes the data lines. Here these two CD becomes data lines. So for these you can see the first 4 set of values A and B are 0, 0. Means when the select line is 0, 0, it will select I0. So we need to generate I0 by using these values of C and D and also with respect to the function they have given. So these two are 1s. So with respect to these, if you put into the table, we will be getting I0, I1, I2, I3 expressions like this. Here you can see not I1, I2, I3 are generated like this. And finally the circuit for 4:1 mux implementation look like this. If there is any mistake over here, please comment below. Let us others know the correct answer. Then explain the working of master slave JK flip-flop with functional table and timing diagram. So this is the master slave flip-flop diagram where one JK flip-flop will be act as a master, other JK flip-flop will be act as a slave. Since the clock will be shared between these two, we need to use a NOT gate here. That makes the first flip-flop will operate in the positive edge, second flip-flop will operate in the negative edge. So you can see here the truth table is not written. We are supposed to write the truth table of the JK flip-flop here. And if you look at the waveform, as the clock generated like this, and when clock is equal to 1 means at the positive edge, when J is equal to 0 and K is equal to 0, master output is 0, here also 0. In the next change you can observe J becomes 1 and K becomes 0. The master will wait for the positive edge to make the output to 1. But slave output changes when the negative edge comes in the next corresponding cycle. This is how master slave flip-flop will work. So this is the waveform for JK flip-flop. Explain universal shift register with the help of logic diagram and mode control table. So this is the universal shift register. You can see here serial input, parallel input, serial input for shifting right and shifting left, and parallel output will be taken over here, and the clock and clear signals are represented. This corresponds to mux and this is a flip-flop. So there are 4 different possibilities here depending on the select lines over here for the muxes. If it is 0, 0, no change. 0, 1 we can shift right, 1, 0 we can shift left, 1, 1 parallelly we can load. Derive the characteristic equation for SRT, D and JK flip-flop with the help of function table. So this is the table, and we put it on the K map, we'll be getting the expression for the Q plus 1. This is the characteristic equation for the JK flip-flop. Similarly for the SR flip-flop here, and then you can see the D flip-flop and T flip-flop. Here the K map is not given. You can write the K map for this also, similarly as SR and JK. Then design a synchronous mod 6 counter using SR flip-flop for the sequence 0, 2, 3, 6, 5 and 1. So here you can see the first state will be 0, 0, 0 as the input sequence is given. Then the next sequence is 2, and then next is 3, then 6, 5 and then 1. So here we need to take the sequence accordingly as it is given in the question. So the states will be like this. And if we write the excitation table of SR flip-flop, since they have given it to implement using SR flip-flop, so SR flip-flop excitation table is this. And correspondingly, if you take the present state as starting with 0, 0, 0, the next state will be 0, 1, 0. So 0, 0, 0 is the present state, the next state will be 0, 1, 0. When this becomes the present state, the next state is 0, 1, 1. And the present state becomes 0, 1, 1, the next state is 1, 1, 0. You can see here, when present state is 0, 1, 1, the next state will be 1, 1, 0. When 1, 1, 0 is the present state, the next state is 1, 0, 1. Similarly, it continues. So here all the different possible values which they are given in the sequence is written. You can also write the different values which are missing out here and take the next state as X. And similarly, we can generate the values for 3 flip-flop inputs. Here we require 3 flip-flops since we need to represent these values with a 3 bits. So here looking at Q1 as well as the next state Q plus 1, we can write S1 and R1. Q1 and Q plus 1 corresponds to S1 R1. So when Q1 is equal to 0, Q plus 1 is equal to 0. Qn is 0, Q plus 1 is 0. S and R values are 0x. So here it is 0x. Now for 0, 0, the excitation table, if you see, again it is 0x. Similarly, for 0 and 1, it is 1, 0. You can see here 0, 1, it is 1, 0. Likewise, you need to write all the values for X, S and R in this table. Then using that S and R values, we can put it into the truth K map to get the expression. So S1 here you can see the sequence is given. So this is 0, 2, 3, 6, 5, 1 as the sequence is given, and the missing terms like 7 and 4 we can put it as X. So this is the K map implementation. We get Q1 bar into Q3 for S1. Similarly for R1 we get Q2 bar, and similarly for S2, R2, R3 and S3 I have simplified like this. If you found any mistake here, please comment below in the video. And then implement that by taking all those S1, R1, S2, R2, S3, R3 using 3 SR flip-flops. So this is one SR flip-flop, this is SR flip-flop, this is also an SR flip-flop, this is also an SR flip-flop. Then realize the 2:1 multiplexer with active low enable, and also write the Verilog program by considering delay time to signal assignment statement with simulation waveform. Here is the 2:1 mux with active low enable, bubble indicating active low enable. It means when enable is equal to 0, the mux will operate depending on the select line and the inputs. So we need to write the truth table as when enable is equal to 1, output will be Z. When enable is equal to 0, if select line is 0, it will select I0. If select line is 1, it will select I1. So the expression will be like this, and we can write the Verilog code in this manner. But we need to introduce the delay as per the question given. So we can introduce the delay over here with respect to the assigned statement. Here I have taken 5 nanoseconds or 5 time units of delay but in the question they have not given any particular delay to be taken. You can also take 5 or 10 time minutes, but you need to show that clearly in the waveform. Here in the waveform you can see the change in Y occurs after 5 time minutes when the input changes. Input will change at one time. After that time, after 5 nanoseconds of delay, output Y is going to be changed. Realize full subtractor circuit using Verilog data flow description. When the data flow Verilog code is asked, you need to write the expression first, and by using that expression we need to implement. So this is a full adder circuit, full adder truth table, full subtractor truth table, and the expression for D as well as B out. And if you write the full subtractor code, it will look like this. Then list all the data types available in Verilog STL and explain any 4 data types with example. So nets, registers, integer, real type, time, array, memories are the different data types, and here the examples also given. You can refer to this, and also you can write a simple Verilog code for this to get the full marks. Explain arithmetic and logical operators with example. This is also with respect to Verilog they have asked. The arithmetic operators are plus, minus, multiplication, into, divided by, modulo, and then power of the other. So you can see the Verilog code here as example. Here within the display statement, we just using those operators, and in the result we are going to get that as a string as well as the result finally. Logical operators. Logical operators are A and B, A or B, and not of A. So this is also a Verilog code corresponds to that as example, and the results you can see over here. Realize the D-latch behavioral description code with circuit diagram waveform. So you can see here the block diagram of D-latch, which has a D input and Q output. There is no clock signal taken here. If you want to take, you can take clock signal with level triggering. You can write the waveform. So D is the input, enable is the input, and Q is the output. Where D and enable are inputs over here in the Verilog code also you can see declare it as inputs, and output reg Q. Why we need to represent it as write it as reg means we are writing in a behavioral description, so the output should be a register. So here I am using if else statement. You can use any other method to write this also. And here is the test bench written. Why test bench is written means they have asked to write the waveform. The waveform is generated according to the values which we are given through the test bench. Write a Verilog structural code for 4-bit ripple carry adder. So single full adder we need to implement first. Using that we need to write a 4-bit full adder Verilog code. So a single full adder you can see at the right, and this is the implementation of 4-bit ripple carry adder using that single full adder. So the Verilog code is like this. At the left side you can see full adder, 1-bit adder, and using that we are designing a ripple carry adder which has 4-bit inputs. Explain the syntax for the following sequential statements in Verilog: for loop, while loop, repeat loop, and forever. So for loop will take initialization and then the condition and then the updating variable, and the things need to be executed within the for block will be put it under begin and end. Similarly, while loop will check the condition and then the statements to be executed will be in between begin and end. In the flowchart you can see that is body. Body corresponds to the logic which we have written in between begin and end. Similarly, repeat and forever begin also can be explained by using the syntax over here. Then the next question, write a Verilog program for 8:1 mux using case statement. 8:1 mux having 8 inputs. Here I have taken input as a vector. This makes easy to write the block diagram and also the case statement. So I corresponds to the input of mux. It has 8 bits. So we can treat it as a 8 input. We can also write like this, or you can take I0, I1, I2 up to I7 separately, and also you can write the multiplexer. And using the case statement means we need to use the concatenation operator for S0, S1, S2. Then only we can write it as a 3-bit variable in the case statement. Then realize JK flip-flop using Verilog behavioral description. So JK flip-flop and the truth table you can see over here. And Verilog behavioral description takes again a always block. Within the always block we need to write the JK flip-flop logic. Here for 0, 0 output will be hold or no change in the state, and for 0, 1 it will reset to 0. For 1, 0 output will be 1, and for 1, 1 it is toggle state. That's why it is not of Q. This is what the answers for model question paper in DSDV subject. Thank you.